audio wasn't recording. Okay, it's recording now. So it's a log function. And what we need to make sure is that what's in the log function must be positive. So the part that's in the log function is everything in this parentheses. The 5 has really nothing to do with the domain. Of course, in the picture, it does have something to do with it. It actually moves the whole graph up 5. But in terms of domain, the x plus 2 is the only thing we have to concern ourselves with. This piece that's inside the function is known as the argument of the function. And this is going to follow the rest of the math that you do. When they talk about the argument of a function, they're talking about the part that's being plugged into the function. Well, in this case, the argument is x plus 2. So what we need to make sure is we need the argument x plus 2 to be greater than 0, right? That's what we need. As long as that's true, we're good to go. This is a linear inequality. So to solve a linear inequality, all we do is move things around. So I can subtract 2 on both sides. X must be greater than negative 2. On a number line, if this is negative 2, to say that I'm greater than negative 2 means I'm to the right of it. Do I include negative 2? No, it's strictly greater, so I want to not include negative 2. So how do I write this answer in interval notation? Negative 2 parentheses, right? And then to infinity. Okay, this is your domain. And yes, you could put x as an element of in front of that if you wanted to. You don't have to. So our answer is an interval. So there's 2 ways to look at this. One way is to say that if you graph this, the picture is only from negative 2 to the right. Another way of looking at it is, if you don't want to think about it in a picture, is that the only numbers that you can plug in for x are things that are bigger than negative 2. So can I plug negative 1 into this? Can I plug negative 1 into this? Yes. That's okay, because I'm adding 2. That would give me positive 1, and then natural log of a positive number, that's okay. So I don't want, the mistake that students will make is they'll say, okay, I remember teacher said you cannot plug negative numbers into logs. And then they'll get an answer that says, yes, you could plug in negative 1. Well, you can plug a negative into a log as long as the argument at the end is positive. Okay, so the argument, everything in there dictates what's going to happen. Okay, let's try another one because that one was a little too straightforward. How about, I'll call it L of m equals log base 2 of m over m plus 2. All right, so I've changed up some things here just to try and confuse you. All right, instead of using f of x, I'm using L of m. L is the name of the function, m is the variable. So let's see what we need to do here. We're talking domain still, okay? I want to find the domain. What do you need to make sure happens? You need what? You need m over m plus 2 to be greater than 0, don't you? That's what you need. And this is not a linear inequality. This is what we call a rational inequality. And let's see if anybody remembers how we solve rational inequalities. You can. We will do that eventually. Set it equal to 0 first. So look, what we do, you have to go back in your notes, okay? We did a section on quadratic inequalities and rational inequalities. They're in your notes, all right? I believe I had the handout notes for these. And what we did is we looked at this as a rational function, and we found the x-intercepts and the vertical asymptotes. Do you remember that idea? Okay, so how would I find the x-intercepts of this? Now, I'm saying x-intercepts, even though our variable is m. Numerator equal to 0. So m equals 0 would be an x-intercept of this. And then the vertical asymptotes, you set the denominator equal to 0. And what's the solution there? -2. Then what we did is we got a number line, and we put those 2 points on it and make sure they're in the proper order. Now, can you have -2? Can you actually plug -2 into this? No, because you'll get division by 0. So you know right away that -2 is not there. So I'm putting an open hole here. Can you plug 0 in? If you plug 0 in, you get 0 on top. But is 0 bigger than 0? No, 0 is 0. So you wouldn't want to plug 0 in because then it wouldn't be positive, would it? So we don't want 0. So the question is, does this stuff work? Does this stuff work? Does this stuff work? So we want to look in those 3 regions. So 3 test points. And those 3 test points we'll plug right into here and see if they're true. Does this kind of ring a bell a little bit? Okay. So let's test -3, -1, and 1. So plug -3 in here, and let's see what we get. -3 over -3 plus 2, is that greater than 0? Yes, that's -3 over -1. That's greater than 0 because negative over negative is positive. So everything over there would work. So I put a check mark in this region. I could, if I want, come in here and shade the line to show you that I'm saying everything over here works. Now try -1. -1, is it going to work? I don't think so. -1 over -1 plus 2, is that bigger than 0? It's -1 over 1, bigger than 0? No. -1 is not bigger than 0, so that does not work. And then you try to plug 1 in. Would 1 work? Yes. So everything to the right. So what is our answer in interval notation? -infinity to -2, parenthesis, union, parenthesis, 0 to infinity, parenthesis. Make sense? That's just to help you see that we have to check 3 different regions. It was just a visual aid to say, hey, look, we're looking here, here, and here. Okay, so the first example I gave you for domain, the previous problem, when we got it, we got a linear inequality, very easy to solve. Greater than 0. Which one are you testing? 1? Hold on. 1, oh, I never plugged it in. It's 1 over 1 plus 2, right? Greater than 0, 1/3. Oh, it's plus 2. Good, okay. So in the second example, we turned out having a rational inequality, right? So linear inequality was the first one, rational inequality, second one. What do you think's coming next? Quadratic inequality. We need to just be prepared to solve those 3 types of things, which is why we studied them earlier to help us with this section a little bit. So for the next example, what if we have Q of t equals log of 4 minus 5t plus t squared. By the way, what's the base of that log? 10, okay? It doesn't matter in terms of domain, right, what the base is. For every log, I'm always going to be looking at the argument, which is here. And I'm going to be saying, okay, I need that argument to be greater than 0, right? And that's what you're going to do for every single log. Domain, you set the argument greater than 0. So how would you like to do this? you can set it equal to 0 and then get your x-intercepts, right? And then you can use the fact that you know it's a parabola that opens either up or down to be able to determine where it's above and below, right? So that's the way I'll do it. So set it to 0 first. And I heard rearrange. I like that idea. So I set it equal to 0. I believe this factors. And then you get two answers, 4 and 1. So that means if I were to graph this, I know that this is where the parabola would hit the x-axis. And I know that this parabola opens which way? Up. So I know it looks like this. And we know from this picture that we are looking for where the parabola, right, this thing, where it was bigger than 0. That means where it is above the x-axis, which is happening out here and out here, right? So, and do I include 4 and 1? No, because I do not want this to be equal to 0. I want it to be greater. So 1 and 4 is where it's equal to 0, so I don't want those points. Everything out this way. Everything out this way. Are there any questions? It's really not anything new we're doing here, right? Other than we have to identify what the argument of the log is and then just use what we've learned already. Yes? What do you mean accept? Just write it in words? Well, that wouldn't be interval notation. And interval notation is the notation that you'll be using in pre-cal, in Cal 1, Cal 2. So it's just get used to that. I mean, we could just write this, x not equal to 1, x not equal to 4, right? And I could say let x be any real number such that it's just not 1 and 4. This is a notation. It's called set builder notation or set notation. This is interval notation. And those two notations, we started in the beginning of the class with using both, but I said we'll stick to the interval. Yes. You can use set notation in, yeah, I mean, you should be comfortable both ways, but this one is really, in my experience, used more. Good? So this means x is allowed to be any number such that x can't be 1 and can't be 4. That's what that's saying. The set of all numbers that satisfy that. Okay, are there any questions on domain? No? Yes. Now, you have to be prepared for things like this. Look, what about a function f of x 1 over trying to see how, well, I don't know if you're quite ready. Let's just do log base 3 square root 1 plus x. This is a little trickier. What? Okay, so there's two issues here. First issue is you have a log. So the argument of the log is here, right? That's your argument? Yes? So you got to make sure that that always stays positive. Yes? But then you also have to be looking at the fact that this whole thing, the whole thing can't be what? 0. So this would be two issues at one time. So you go and you look at each one individually. So first let's look at the yellow part. I need the square root of 1 plus x to be greater than 0, right? because the argument has to be positive. Now, can I square both sides here? Yes, but the reason why is because there's a 0 over here. All right? Basically, the only thing that can ever come out of square root is a positive number. Right? You can never take the square root of something and get a negative answer unless you have imaginary numbers. So we're not doing that. So I will say it's okay to do that. Square both sides. When you square 0, 0 squared 0. And now what type of thing is this? Linear inequality. So just subtract 1 from both sides. So x must be greater than -1. That's the first thing, right? That's the first thing. The other thing I need is I need that the entire denominator, right, cannot be equal to 0. Right? How would that happen? Yeah, that's right. You could. Couldn't I try and figure out when this happens by doing the loop? 3 raised to this must equal this. Do you agree? 3 raised to this must equal this. So why don't I do that? 3 raised to the 0 must equal, well, we don't want it to equal, right? This? Nope, you've got to solve for x. So what's 3 to the 0? 1. Now square both sides. So x cannot be what? 0, subtracting 1 on both sides. Let's just see what happens if we plug in. Let's just check it here. Plug 0 in here. 1 plus 0 is 1. What's the square root of 1? 1. So what we have is this, log base 3, 1. Does that equal 0? 3 to what power is 1? 0. Right? That's what this means. 3 to what power is 1? 0. So yes, this is 0. So yeah, we don't want that happening. So if we try and plug 0 into this, we get division by 0, don't we? So let's combine these two answers. The first one says, I can be anything I want as long as it's bigger than or to the right of -1, right? This one is saying, here's 0. You just can't be 0. You can be anything else, but not 0. Do you all see the difference between the two? What we're looking for is what they have in common, where they overlap. So it might be good to put 0 in here. Say I can't have that, right? I can have everything to the left and everything to the right. Agreed? I know it's getting messy. But where do they overlap each other? Right in here, right? And then how about out here? But we want everything in there, right? Everything. So how would I say this? No, we don't want this. They don't both exist here, right? It's bigger than -1 meant only to the right of -1. So it's where they're on top of each other, where they intersect each other. Do y'all follow that or not? Okay. All right. So -1 to 0. Don't include either one, right? Union 0 to infinity. So you see that problem was a little more complicated, wasn't it? It wasn't just as simple as, oh, just look at the argument, because if that log is part of something else, then you have to also take that into account. I don't think I'll go any further than that on a test. So, okay, so that's domains. And now the next thing that we want to talk about today are solving log equations, which we actually just did. So this will be 6, 4, 11. solving log equations. I'm going to give you some examples. Solve the following. Log base 3 of x minus 2 equals 4. Okay, so this is an equation, right? It's an equation. It has a variable x. We want to solve for that x. Right now, the x is trapped inside of the log, right? It's inside the argument of a log. We, at the end of our problem, need to be able to say x equals something, right? So we need the x to come out of the log. The only way to get the x out of the log is to come in and do the loop. So we're going to rewrite this from log form to exponential form. So the loop said what? 3 raised to the 4 must be this. So I'm just going to write that down. 3 to the 4 must be x minus 2. And that is 3 raised to the 4, right? That is not 3 times 4. So 3 times 3 times 3 times 3 is 81. And then add 2 to both sides, and you get 83. 83. Now, there is a drawback to this. We have to check our answers. The reason we have to check our answers is because we know that you can't get a negative inside the argument of a log, right? We know that you can't have that. So let's just do a quick check. Does 83 work? 83 minus 2 is 81. So what we're saying is log base 3, 81. That's okay. I can have 81 in there. And now let's just think about it. This is saying 3 to what power is 81? 4. And that's what the other side was. So it all looks okay. So yes, this is 4. How about natural log of 2x minus 5 equals 2. Tell me what x needs to be. So how do we do this? You can still do the loop, but what are you going to do the loop with? E. So this is, remember I said the notation is different for natural log and they don't write the base down there? You need to remember that there's an E down there. Now, I've seen students just throw an E down there, and I understand what you're doing, but really you're supposed to write, just rewrite it log base E like this. That's the proper way to rewrite this. Log base E, this is the same exact problem. Now, do your loop. E squared must be this. E squared must be 2x minus 5. So we could get on our calculator and figure out what E squared is, but the book asks you to get what's called the exact answer. So all we want to do is just isolate x now. So don't go to your calculator. Isolate x, you would add 5 first, right? So how about, I'm going to bring this up here. On the left side, I'll have e squared. I added 5, so e squared plus 5. Whatever that is, I don't even care what it is, right? And then divide both sides by 2. So it'll be e squared plus 5 over 2. That's what x is. Now, if you want to know if it works, to check it, you would have to get on your calculator to make sure that this number, when plugged in here, works. So e squared is 7 point something, plus 5 is like 12 point something, divided by 2 is like 6 point something. So 6 point something plugged in right here. It's going to give you like 12. So you should minus 5. It should be positive. So it's okay. It's an okay solution. Pardon? Lowercase on, are you saying on your calculator? Oh, yes, lowercase e. Yes. And I should also point out to you that on your calculator, you'll have an E key, and there's also an E key that looks like this, or you may have seen that before. And those are totally different things, all right? This E right here, a lot of times you'll see it like when you type something in the calculator, it'll say like 4.2 E7. You ever seen that on your calculator before? No? What this means is you take the 4.2 and you move the decimal point 7 places to the right. 1, 2, 3, 4, 5, 6, 7. Move your decimal. 4, 2, 1, 2, 3, 4, 5, 6. So this, if 4.2 E7 really means 42 million on a calculator. So that E is telling you how many decimals to move, how many places to move your decimal point. If it's a negative number, guess what you do? You move the decimal the other direction. So any of you who take like chemistry, biology classes where you're doing these things and pH and stuff, and you get these answers that are like 0.000437, if on your calculator it's probably going to say like 4.37 E and then 2, 3, 4, 5, negative 5. These two answers are the same. So this E is nothing, has nothing to do with this E. This is the natural base. This is just helping us do scientific notation. All right, another example. Solve this. What is natural log, or no, we've already done natural log. What is log base 7 of 7 to the x squared minus x equals 2. Now that's starting to look pretty ugly, isn't it? So there's a couple of ways we could do this. Could you do the loop? Okay, so I would start with the 7. I would say 7 squared must be equal to 7 raised to the x squared minus x, right? We would set the tops equal to each other. So if you did the loop, it would be this. 7 squared must be equal to 7 to the x squared minus x. Then the fact that these both have the same base means you can rewrite it as 2 equals x squared minus x. Right? We did that. That was part of your homework, actually. Try and get the same base on both sides so you could set the tops equal to each other. This is a quadratic equation. This is just x squared minus x minus 2 equals 0. And that factors to give you x minus 2, x plus 1 equals 0, which gives you two answers, 2 and negative 1. Now, that's one approach. There's nothing wrong with this approach. You get the two answers. The other approach relies on something we did last class. We talked about properties. No, I thought we talked about properties. Oh, this right here. Yep. They're inverses, right? Remember this? If I take log base 2 of x and I put it together with 2 to the x, what comes out? If I put log base 2 and I put 2 to the x inside of it, it just spits out what's up here, right? you could have realized during this problem that I have log base 7 and I'm plugging into it 7 to the something. And so you could have said that this log base 7 wipes out this, and all that comes out is what's up here. So in other words, the left side of this is looking at a different way, the left side of this all just becomes x squared minus x, because these kill each other off. And then the right side is still 2. And now you're at this same step, right? Without doing a loop. How do they do that? Because they're inverses, right? Whatever 7 to the something does, log base 7 comes back and undoes it. So if I'm doing 7 to this junk and then come in here and undo it, the junk is what starts, right? Dirty car, clean. Now back to dirty. But the loop, I think, is more powerful because, you know, you don't get hung up on stuff like that. Okay, questions over solving these equations? They're going to get more complicated. We actually have an entire section called Solving Exponential and Logarithmic Equations. This is just to get us warmed up to them, all right? So with that in mind, let's talk about a problem that I did a long time ago. It was like 2 classes ago. It was day 18, I believe. Try and find this. No, we were trying to solve an equation with log. It might have been the last class. Let me see. Oh yeah, solving equations. Here it is. Here it is. I left a question mark on it. Where was it? I thought I gave you one where we couldn't solve it. Okay, well, I'm not going to sit here and look for it all day. I thought I gave you one. Solving where am I? 12? 6, 4, 12. Solving exponential. Was it what? Yes. Oh, well. Did I leave it as an unanswered question? Yes, there it is. 4 to the 3x plus 1 equals 5. Four to the 3x plus 1 equals 5. I knew I wasn't going crazy. Okay, so I gave that to us on an earlier class when we were doing that thing where we were trying to get the bases to look the same and then match the tops together, right? You had a whole homework assignment on that. And I said, but a problem like this, we can't do it because we can't get these bases to be the same. Like 5, there's no way you can rewrite 5 as a power of 4 or power of what, like 2? Because 4 is 2 squared. So there's no way you can get the bases to match, right? I said, what do we do? Well, we can come in here and try and do something with logs, maybe? Can I rewrite this as a log? Okay, how can I rewrite it as a log? Log base 4, 5 equals 3x plus 1, right? That's rewritten. Now the question still remains, what is this, right? This means 4 to what power is 5? 4 to what power is 5? Who knows, right? We still don't know that. Do y'all agree? We don't know what that is. But do you see that I can isolate x now? Do you see I have a way of getting x here by itself? Now, I'm going to leave this as an open question. We're going to answer that. We're going to answer that in the next section. All right? Like, how do we figure this out? But if I want to isolate x, I can just do what? Subtract 1 on both sides, and then divide by 3. So I've solved for x, but I still don't know what this is. The moral of the story here, the only reason I wanted to do this, is that when we were doing this before, we really had no way of doing it. We were trying to get the base to be the same. We said no way. Now at least we have a way of getting x by itself if we can figure out what this is. I think that leads us into the next section very nicely, because the next section is going to give us a way of doing that right there. Okay? But we use the log to be able to rewrite it to have x isolated now. All right, so let's go to, let me give you your homework out of this section. So this is still a question. Homework, page 447, 37 through 47 odds. Those are all domain problems. And then 87 through 97 odd. Y'all doing okay? Yeah. Okay, let's do 6.5. Properties of logs. Yep. I'm going to put a couple little stars here. So how many of you are going to take Cal 1 at some point in time? Show of hands. Okay, Cal 2. All right. And beyond, who knows, right? These properties of logs, this is the time you're going to see them. All right? This is the time you will see them. There will not be a refresher on this. In pre-cal, you won't really talk about, I mean, you won't really have these come up much. So you have to remember them, because when you get to Cal 1, it's assumed that you know the properties of logs, and they're used extensively. So you get like an entire class between now and Cal 1 where you don't see it, and then, you know, all of a sudden it's there again. You're like, I don't remember the properties of logs. So this is very important that you at least know they exist and know where to go back in your notes to find them. All right? All right, so there are lots of properties of logs. I believe, if you flip back to 19, no, special functions, 19, 20. Let's just start with them. I'll just start giving you properties, okay? First property, log base anything of 1 equals what? What is this asking you?
What power does A have?
Yes. A to what power is 1? 0. And that doesn't matter. That doesn't matter what A is, right? Assuming A is positive and not 1. I mean, assuming that it's a true logarithm, A has to be positive and not 1. So if someone gives you a log base 4, log base 10, log base E, which would be natural log, doesn't matter what the base is. If you try to plug 1 into any log, it spits out 0. Yes? So to the side of this, I'm going to write the analogy with the specific case for the natural log. So this is saying natural log of 1 would be what? right? If I replace this a with e, it's natural log, right? Natural log of 1 is 0. Okay, that should be like 1 plus 1 is 2. 1 plus 1 is 2. Natural log of 1 is 0. You don't want to be like, okay, what's natural log of 1 and be all like grabbing your calculator. Okay, you don't want that. Okay, next property. Log base anything of that same thing is what? 1. Because this is saying a to what power is a? 1. A to the first power. Now tell me what this property is. What the hell am I doing? Property 1, sorry, this would be property 2. Tell me what I'm doing here. Look, I told you the natural law is used a lot, right? A lot. So this is the general formula. This is the general property applies to any log, but I want you to see it with natural logs. So I'm giving you a specific example of this property over here with the natural log, because it's seen so much. All right, so natural log of 1 is 0. So how would I write this property over here? ln, but not a. See, because for this to work, the base in this have to be the same. So it would be ln what? E. Exactly. Is 1. The natural log of E is 1. The natural log of E is 1. Because what this really means is log base E of E, right? So you're saying E to what power is E? 1. Again, that's got to turn out to be like 1 plus 1 is 2. Natural log of E is 1. Third property. Log base A of A to the X is X. Good. Because A to what power is A to the X power? X. So how is that written over here? Natural log of E to the X is X. It's supposed to be a 3. I don't know. Get your glasses checked. It was 3. So look at property 2. Go take care of that. We actually don't even need property 2, do we? Because this actually is more general. See, if I replace that X with 1, isn't E to the 1 just E? So isn't this just with a 1 up here, and so our answer is just whatever was up there? So, just pointing it out. We don't need property 2, but it's most books do. Okay, now that property works the other way around, although not as widely used. A to the log base A of X also equals X. And that means over here that what? E to the natural log X equals X. This is happening because these are inverse functions. When you put E together with the natural log, it spits out what you started with. When you put natural log together with E, it spits out what you started with. So those are the compositions of the two functions both ways. Understand? This one, E is going inside of log. This one, log is going inside of E. Or it's going to the exponent, which means the same thing. Okay? All right, so those are the first 4 basic properties. Now, starting to get some weird ones. Log base A of M times N equals log base A of M plus log base A of n. Very, very interesting property of logs. So let's see what this is saying happens. If you have a logarithm, right? Notice I have a single logarithm here. Inside of that logarithm, I have two things being multiplied. It is saying that you can split this into two logarithms and put addition between the two logs. Here's what's not happening. You are not distributing this through because it is not multiplication. This is a logarithm. Log A is not like a number that you multiply through parentheses. It's the function. This is a property of the function. If you try and put two things inside of it that are multiplied, you can split it into two. Not many other functions behave like that. Logarithms do. Now, how could I write that over here? Natural log of m times n should turn into natural log of m plus natural log of n. Now, this property is used a lot, all right, in math. As you continue to move through, this is used a lot. And the way you read it, I want you to read it two ways because it's an equation. You can go both directions. If you ever have a single logarithm and you'd like to split it into two logarithms, you can, as long as this was multiplication in here. If you have two logarithms with addition between them, you can compress them together into a single logarithm. Sometimes you're trying to go from the left to the right. Sometimes you're trying to go from the right to the left. It depends on the problem. Over here, same thing, right? Natural log of a product is the sum of two natural logs. Or you can go, the sum of two natural logs is a single log with product inside. Now, what do you think happens if I do this log base A, and this time I do division, m over n, instead of m times n? What does your instinct tell you? You're going to subtract them instead of add them. So you're going to get log base A of m minus log base A of n. Now, the order matters here, right? M was on top, so m goes first. N is on the bottom, n goes second. Because subtraction, the order matters in subtraction, right? 5 minus 4 is not 4 minus 5. So you have to do the log of the top one minus the log of the bottom one. Y'all okay with that? Look, you want to see one of the most common mistakes on this? I hate showing mistakes. Yes. And it's a pretty normal mistake because you think, okay, I've got log with division. That just means take the log of the top, divide by the log of the bottom. That is not the case. Okay, so don't want that. Division inside of a single log becomes subtraction of two logs. Or the other way around. If you have subtraction, you go back to this. All right, next thing. ln of m over n is equal to ln m minus ln n. Yes. The book uses m and n. I've always used x and y, but I'm just following what the book does. Okay, we doing all right? We got some more. Yep, hold on. See if I can. There. This is a Cal 2 problem. Okay? I want you to notice the first step of this problem. Forget all this in here, okay? Just notice the first step. This right here, natural log of m over n, right? M over n equals natural log of m minus natural log of n. The first step of this problem was to pull that, to use the property of logs, that if you have a single log with division, it can split into two logs with subtraction, right? That's just the first step of that problem. And that, I promise you, we didn't review, okay? We didn't go back and review properties of logs. We just did it, all right? So it's used later. What's that? This is known as an infinite series. We're trying to figure out what this adds up to be. So this means add these things up forever and see if it converges to a number, and it actually doesn't. It diverges. It becomes infinite. But they don't always do that. Okay. All right, next property. Seven. Log base A of m to the r power equals r times log base A of m. And I'm going to put a blue with red star next to that. That's my favorite property of logs. And I'm starring it because it's probably the most powerful one. It's the one that really allows us to do some good stuff. Yeah. So what happens here? What is this property saying? You have log base A, and your argument is something to a power, right? What is it saying you can do with this power? Just pull it out in front. Drop it in front. Just pull it in front of the log. It just pops out of nowhere. Now, I'll explain why it does that in a second, but let's write it down for the natural log. This is saying natural log of m to the r is equal to what? R natural log of m, and that's it. Big time, that property right there. So why is it true? Let me try and explain. If I take, I'll do it with natural log of m to the r, doesn't that mean natural log of m times m times m times m, and how many of them would I have? How many of these m's would I have? I'd have r of them, right? And each of these multiplications, didn't we say that if you had multiplication inside a log, you could split it up into two logs? Yes? So I could look at this being one thing, and this whole thing is my next thing. So I could split it into two logs. Natural log of m plus natural log of m times m all the way until I get out to m. That's this pink part, right, over here? But then I could take that and say the same thing, couldn't I? And peel one of them off again. And I could keep doing that. And I could do it for all of them, couldn't I? And keep on peeling them off. So I have an apple plus an apple plus an apple plus an apple. How many of them do I have? R of them. This is R apples. This is R apples. Yeah. So that's the property. You see it? You see that? Because it is finite. Your number just pops out. Yep. So if you had like natural log of x cubed, that's the same as 3 times natural log of x. Yeah. Would you like to see that one in action? I mean, like, show you an example of that being used? Yeah, not a bad idea. Ah, look, I opened up right to it. I didn't even mean for that to happen. Couldn't have planned it. Okay, so the question here is in a Calculus 1 class. This right here in the front means to tell me what's happening if you let x get close to 0. Now, if you just try and replace 0 in here, you have major problems. First of all, what is sine of 0? Well, you haven't taken pre-cal, so I wouldn't expect you to know what sine of 0 is. Sine is a trig function. When you plug 0 into sine, you get 0. Okay, so that's 0. This is 0. And then raised to the what? Let x be 0? 0. What's 0 raised to the 0? That's a major problem. You have to figure out what it is. I mean, you can't plug 0 in here. Okay, basically 0 to the 0 is undefined. It's like division by 0. But this is doing something, okay? It is actually headed towards something. It's approaching something. If I were to graph that, go ahead, take off. I can see you got to go. It's good. I'll tell you all the best thing in a second. The best thing. What was it? It was sine x raised to the x, right? If I graph this, this graph's weird, but what's happening as I approach 0? The graph looks like it wants to get closer to 1, doesn't it? As I get close to 0 on the x-axis, as I'm moving towards that, the graph wants to get close to 1. Somehow, I need to figure out that the answer is 1. So the first thing that I do in this problem is I call what I'm trying to figure out, I call it y. And then I take the natural log of both sides. And then check this out, right here. That step is the property I just showed you. That gets the x out of here. And then from there, I go on, do the rest, and I don't remember, we got stuck, so we had to come back the next class and finish it off. What was that, 17, day 18, I came in. Did I? Oh, I answered examples first. Oh, here it is. No? I know I resolved it. There it is. Okay, so I had picked up the work, and we got at the end, the answer was 1. So, yeah. But no, I wanted you to see the property being used, right? That's it. And then the big framework of the calculus problem, I'm not asking you to understand that. I'm trying to get you to buy into the idea that the properties are important, because you can't do calculus without properties of logs. So that's why we're learning them. Okay. So there are your properties. No, that's it. All right, so let's try and play with these a little bit. This will be I said 6.5 properties of logs. I forgot to say 6.5.1. So that 6.5.1 was all the properties. Now let's do 6.5.2, which will be examples. I want you to rewrite this as a sum or difference of logs. This is what's known as expanding. Okay, so here it is. Natural log, square root of x times x squared minus 1. Go ahead. Is there something going on I need to know about? Is there like a festival or something? No? Okay. All right, how many logarithms do you see here? How many logs do you see? 2, 1? I see one logarithm right there. Do you see it? Right there. It's one logarithm. We want to rewrite this as the sum or difference of logs, plural. Yes? If I wrote plus natural log x like that, right? No. Yeah, sometimes we make it harder, you know, try and think I'm asking something more complicated. But no, just how many logarithms do you see? Just one. But you can make it into more logs. And that's the goal here, is to try and use the properties of logs to rewrite it where we have addition and subtraction of multiple logs. So the first thing I'm going to do is to realize that the argument of this logarithm has a square root, right? Which is the same as raising something to the 1/2 power. So this square root right here is controlling everything inside of it, isn't it? So that means that this parenthesis, right, that parenthesis around everything to the 1/2 is the square root. Yes. Now, what would you like to do with this? Anything? You want to separate these because it's multiplication between them? You can split it into 2 logs? Yes, but you got to get the 1/2, you got to resolve the 1/2 first. So why did I write the 1/2 out here? So I could use property 7 to pop the power out front. Okay, so I'm going to pop the power out front. That's property 7 right here. I'm going to circle. I'm using property 7 to do this. This becomes 1/2 times natural log of x times x squared minus 1. Any questions there? The 1/2 came out. 7. I'm telling you that I used, where did my favorite property, yes. This property right here, 7. Pull that up. I'm sorry? Just the whole idea that you can pull a power out like that is my. I mean, we're making it sound like I live for that property. I mean, it's just I like that property. It's not like I'm been looking forward to today all semester or anything, you know. Yeah, I'm sure. Okay, so now that that's out, I can look at this inside right here. I'll make it a big dot. That right there is multiplication. Yes? So I can split this single log into 2 logs. But what about the 1/2 in front? It's got to go to both, right? Because it's like a multiplication. So if this is going to turn into 2 things, that 1/2 has to go to both of them. So watch what I write here. And what property am I using right here? 5. Property 5 allows me to take that single log. Here's what I'll do, just so you can see it. That single log becomes natural log of x plus, right? Natural log of x squared minus 1. You'll see it? This right here became this right here. Now, the 1/2 is still out here. I'm going to distribute the 1/2 through to both. You could have done it all at one time. I was just trying to show you. It's a great idea. Good suggestion.
No.
Too late. Too late.
I said that we should do a bonus question about your favorite question.
I thought you were requesting to memorize all the properties of logs. Historically, I've never allowed students to have a cheat sheet with those. So, I mean, you should know them, right? This is the whole point. I was trying to convince you in Cal 2, Cal 1, you're supposed to know these. If you can't know them now, how are you going to know them later? Yeah. Well, if you've learned it, then you don't need a cheat sheet. But they're going to forget it. They're going to forget it. If they never had to remember it, if they never had to remember it, they'll forget it. And you'll forget it too.
Extra points
right?
memorized.
Come on. Y'all got to hold yourself to a higher standard. You are capable of learning 7 formulas and memorizing them and being able to reproduce them for a test. You're capable of that. You are. If you think you're not, then you should question yourself. As an engineer, as whatever it is you're going into, you've got to believe that you can memorize something like 7 formulas, right? Look, I'm not a memory guy, okay? I couldn't stand organic chemistry, all that, biology, memorizing all of it. No, my brain doesn't want to work that way, okay? There's a lot in this class I've let you use on tests, a lot. Steps on how to graph functions, all those things I've let you use. I'm trying to tell you that these log properties, you've got to know like 1 plus 1. That's because you need to know them like 1 plus 1 to do well in calculus. So this is one place where I would want you to know them. At least for that test, you showed that you knew them that day. So let's go with that as the plan, all right? And the bonus question. Okay, are we done? Have we split this into a sum or difference of logs? Well, I've got 2 logs now. Yes? There's no equation, so we're not solving, right? It's just, this is a rewriting of things. That's all it is. It's just kind of like making it look different than it started. Okay, it looks done, but we're not. Because you recognize in here something? X squared minus 1 is a difference of squares. So that actually turns into x plus 1 times, right, x minus 1. And now we have another multiplication in there, don't we? And since we have another multiplication, we have like an m times n, and so this log now splits into 2 logs. And what happens with the 1/2 in front? It goes to both. So you have 1/2 natural log x plus 1/2 natural log what? X plus 1, and then plus 1/2 natural log x minus 1. Now you are done. So believe it or not, these expressions are equivalent. This is equivalent to this. All right? Solve, what do you mean? Well, yeah, that would be, if we were solving for x, we would need it to be equal to something like equal to 10. And we would not expand it. We would have left it like this. Okay, we will solve equations. We will solve this for x later. But you know what we'll do? First step is we'll go backwards. We're going to put it all back together, and we're going to get it to this. Because once it's here, we can do the loop. Once we get it to a single log, we can do a loop. But in different classes, you have to go one way or the other way. If I'm looking at this and trying to solve it, I want to go back up. If I'm in a calculus class and I'm trying to do something, most of the time I want to go from here down to here. Yeah, it's just application of the properties. Go ahead. I think I'm going to go too. Everyone else is going. I'm going to take off. Y'all just sit here and make up your own problems. What's up? The square root means the same as raising something to the 1/2. So I'm using this, that if you take the nth root of something, it's the same as raising it to the 1/n. So if I have the square root of x, that's x to the 1/2. Now, I had this whole thing to the 1/2, and then the 1/2 came out. Is that okay? All right. All right, let's do another one. Log base 4 cube root x squared plus 1 over, all right, x cubed times x plus 1 to the 5th. I would like us to rewrite this as the sum of, or difference of several logs. So in other words, expand. Expand this. You want to take that cube root and rewrite this thing as being raised to the what? Okay, that's fair. Now, right now I have not used any properties of logs, have I? No, I'm just using properties of exponents and just what they mean, just notation-wise. Did that stack of quizzes get around? Where did it go? Is that it right there? Now what? Don't worry about it. Don't go through it now. This is an important example. You can use properties, but what do you want to use? 6, what does 6 do? Division? You want to take care of the division? Why not pull the 1/3 out? That 1/3 would have to be on everything, and it's just on the numerator, okay? In the last problem, that 1/2 was on everything, so we pulled it out right away. Here, that 1/3 is only affecting the top. So you need to see, yes, property 6 is correct. You need to see that you have a numerator and a denominator, an m and an n, right? That's what you have? So we're going to change this from log base a of m over n to property 6 says log base 4 of the x squared plus 1 to the 1/3 minus, now a new log, of what? X cubed times x plus 1 to the 5th. Now notice how I did this. This denominator, x cubed times x plus 1 to the 5th, I put that inside of a log, right? So I put parentheses around it. What now? You can use 7 where? This one right here, can I use 7? Can I bring this out front right now? Yes. Because you cannot do anything to x squared plus 1, right? It can't factor out. But, I mean, even if you could, the 1/3 is acting on the whole thing, so you could pop it out. Could you do 7 on this one? The power that you have has to be acting on everything. So 3, yeah, but what about the 5? So they're not the same, but there's multiplication between the two. So I have like an m here, and this whole thing is like an n. And when you have multiplication of two things inside of a single log, it splits into 2 logs with addition between them, right? But what about the minus in front? The minus will have to go through to both. Yeah. No, no imaginaries. We're not touching imaginaries.
You could probably do this, but probably could you put x squared out front and then just make x plus 1 to the squared? You know, like I'm sorry, take the cube, make it x inside x times x plus 1 to the 2, and then pop out the 3 out front, because they both have to go to the 3 power.
I see what you're saying. You would have to rewrite this as x plus 1 cubed times x plus 1 squared. Yeah, it would be. I think it would be harder that way. Yeah, it would be more complicated. So I've got a couple of things going on here. I've got the 1/3 coming out on the first log, and then I have minus. You said you wanted me to split this into 2 logs, right? And you said it turned into plus, right, when I did the 2 logs here? But that minus had to go through to both? So minus minus Another log? That okay? Now the 3 can come out because it's acting on the x, and the 5 can come out. And I believe we'll be done. 1/3 log base 4 x squared plus 1 minus 3 log base 4 x minus 5 log base 4 x plus 1. Yeah. If you can isolate that exponent on one thing, yes, you want to drop it out. Yeah. Mm-hmm. You cannot separate this because it's addition inside of a log. There's no formula to split up addition. It's only if it's multiplication in here. A little side note here, just be careful on something. So notation here. Are these the same? No? They are not the same, okay? What I'm getting at is that the use of the parentheses is necessary. It's not something we're doing just for fun. This means log base 4 of x, whatever that is, then add 1 after you're done with the log part. This is log base 4 of x plus 1. You actually do the argument first, then figure out the log. So you cannot leave parentheses off. Notice how I have x plus 1 here with parentheses? If I left those parentheses off, I would be incorrect. All right, now I didn't put parentheses around this x because it's just a single term, x. So I don't need another set of parentheses there. Could I put parentheses right there? Yes, it wouldn't be wrong. But they're not necessary. Here they're necessary. Here they're necessary. All right. Let's try to see if we can go the other direction. I would like for you to condense this. That's the other direction. You think this is easier? Okay, so how are we going to do it? You're going to go backwards from what we were doing before. Start with the things that are out front, 3's, and push them up as powers. Natural log of x cubed. Next one, minus. Is that okay? Minus natural log of x minus 2 to the 1/4 plus just natural log of 4. So the powers got pushed up, right? Now, what? You could write that as a root. I'll do it on the next step. You could have wrote 4th root if you wanted. So what am I going to do? Am I going to put these 2 logs together into one log, or am I going to put these 2 together in one log? Which 2? You said those 2. I'm not sure what those 2. These 2? Those 2? These? That one? No. Does it? Absolutely matters. How what? Order of operations. Order of operations. What are the order of operations? But remember, multiplication, division is always done left to right. Addition, subtraction is done left to right. Uh-oh, I'm getting that look. Did we do this problem at the beginning of class? We didn't talk about this at the beginning of our class? What is that? What do you do first? Division, multiplication. So most people would say here, a lot of people would say that the answer is 1. Because they used, please excuse my dear Aunt Sally or something like that. They always think multiplication always goes before division. That's not correct. It's always multiplication or division, whichever appears first as you read from left to right. So you should go 12 divided by 3 first. That's 4. Then times 4. The answer is 16. If it helps you, yeah. It's a bonus question. Okay. And addition, subtraction works the same way. You go from left to right. So I'm going to do subtraction first. I'm going to do this first. So I'm going to put those two together. So that's going to turn into what? A single log, right? A single log. Do not write natural log over natural log. That is wrong. It's a single log. Inside of it goes division. X cubed over x minus 2 to the 1/4, which I'll write as the 4th root of x minus 2. Is that all right? What is still sitting out here? Plus natural log 4. Now you have 2 logs, right? 2 logs can go together into a single log. Here's my single log. And this time it's going to be something times something, right? It's this whole thing times what? 4. Which I would never write that way. I would just write 4x cubed over square root, or 4th root of x minus 2. And now you have a single logarithm. You started with 3 logarithms. You've condensed it all the way down to a single logarithm. Yeah, maybe. Depends on you, you know. All right, we've got about 9 minutes. You don't? You do expand. You do expand, yeah. The one I showed you, that Cal 2 problem, where the first thing they did was they took natural log of something over something, and they split it into 2 logs. That's expanding. But earlier in that Cal 2 class, we did it also with other stuff, even more expanding. So it's both. It depends on what class you're in, yeah. So I'll show you, because we're out of time, I'm going to let you go a little early. But I do want to show you one thing and give you a homework assignment. We are not done with this section. We still have more properties. Not properties, but I told you we were going to be able to solve that problem. We have not done that. So, but to get you going on homework, page 457. Oh, wow. I'd like for you to try to mess with 37. Wow. Through 51 odds. And then try 57 through 63 odds. As you'll see, that they get kind of messy. The top one is 37 through 51 is expanding, and then 57 through 63 is condensing. They say it in another word. They say it like rewrite as a sum or difference, or put together as a single log. Yeah, that's on top of the other one. I'll let y'all go. Have a great day.